Good.
Pointer doesn't like do anything here.
Yeah.
That's it, therefore.
All right, so just welcome everyone to second or one of the few ANC seminars this term. Okay, today we are very happy to have Mahsa Derakhshan, who's an assistant professor at Northeastern, telling us about the stochastic vertex cover. Go ahead.
Everyone, thank you for joining. I'm going to talk about approximation algorithms for minimum vertex cover on stochastic graphs. This is based on a joint work with Derakhshan and Berkeley. Okay. So, what are stochastic graphs? We can look at them as a generalization of random graphs, where edges can exist with different probability. Right? So we have a base graph, G. It may not contain some of the edges. And then we also have an existence probability for any edge in G. Then these edges will be realized independently, forming the realized subgraph or the stochastic graph G star. So if G were to be a complete graph and P was the same for all the edges, that would be simply a random graph. Okay. Say here, this is our G, just as an example. And then say PE is the same for all the edges. It's our base graph. Then a realization of that G star looks something like this. Contains each edge independently with probability time. Now, in the setting we consider today, we don't know all the edges in advance. Instead, we have these existence probabilities, and what we can do to know whether an edge exists or not is to query the edge. And after querying the edge, we see whether it exists or not. And our goal is to have a few number of queries, preferably O of n total, to find a good approximate solution for whatever problem we are studying in this setting. Okay. And the benchmark that we compare our algorithms with is the omniscient optimal solution, which is the solution you can find if you know the realization of all the edges in advance. So basically what we are trying to do is that we are interested in finding a sparse subgraph of G such that after querying only edges of that subgraph, we can find a good approximate solution. Some of the problems studied in this set.
Sorry. Take the blame.
Don't worry. Yeah, some of the problems that here are pneumospheric trees, packing problems, shorter path, matching Smith studied significantly, and today I'm going to talk about minimum vertex cover. And you probably all know, but the vertex just
sorry, can I go back to the previous slide just as I understand the setting? Sorry. Okay, so you're given a graph and you know the graph. No, you can only have query access to the edges of the graph, so you discover the graph as you go along.
Yes. So we have a base graph originally, right? So that meaning that knowing that base graph, you know that some edges don't exist.
Right. Okay.
So now for the remaining edges that are in G, you have an existence probability. And they will exist independently in G star. Now, querying an edge, right? You take an edge from G and you query it. It tells you whether the edge exists in G star or not. I also refer to that as the edge is realized, the edge exists.
Okay. And then here, then you want to find an approximate solution to some problem, like as you're saying, with a small number. Okay. And then the omniscient optimal solution in G star. This is like the, okay.
So if you knew everything, like if you could query everything, right?
Okay.
And then what's the solution? Thank you. Vertex cover is a subset of vertices that contains at least one endpoint of any edge, and we are interested in finding small vertex covers. So the known results for minimum vertex cover in this setting for general graphs. Before our work, there was 2 plus epsilon algorithm using n times polynomial queries. This is tied for getting any constant approximation. For bipartite graphs, this is slightly better. And if we allow exponential dependency in 1/p, then you can get Mahsa approximation. But we are interested in tight number queries. And we know that under unit gains conjecture, you cannot get better than 2 approximate solution for vertex cover in general graphs, right? So if we are trying to do better than that, we should allow exponential or here unlimited computational power, right? So the question we asked today is whether allowing unlimited computational power would let us find better than 2 approximate minimum vertex, 2 approximation, design better than 2 approximation algorithms for minimum vertex cover in this setting, and we are interested in having tight number of queries.
Did we know anything even if we don't want tight number of queries in general graphs?
Yes, so that one.
No, sorry, better than.
Oh,
that's
so this is
bipartite.
for bipartite graphs, yeah, no, for general graphs. Yeah, I'm not sure that's the mean. So our main result here is a 1.5, almost 1.5 approximation algorithm using tight number of queries. Oh, I didn't tell you what P is. It's the minimum probability over like all the edges. Right? The smallest PE over all the edges. And we also show that if you want to get, if you want to improve better than, if you want to have algorithms, if you want to get approximation ratios better than 1.5, that's not possible if at least around O of n edges are allowed to be realized in a correlated way. This is based on a structure for first presented by Seper, Sanjeev, and yes, okay, in a paper for stochastic matching. I believe that shows that you cannot get better than 2/3 for matching if you allow n correlated edges. We have the same construction on the probability certain. Let's go over the problem again. We have our input graph, our base graph, probability of existence for NHP sub E, and we can query the edges to see whether they exist or not. And we are interested to find a small vertex cover using few queries. Okay, something that I need to note here is that I want my solution to be fast always. So the vertex, the subset. So any edge that I do not query should be covered, right? Because there's a chance that that edge may be realized, and in that case, the solution I output will not be valid. Right? So put it differently, I want to pick a sparse subgraph edge of my input graph, such that after I query edge, and I see the realization of these edges and find the minimum vertex covers of the realized edges here and any edge that I didn't query. That should be a good that should give me a good approximation. So we define the approximation ratio as the expected size of the solution that we find over the expected size of the optimal solution. And why do we have expectation here? Because opt itself is a random variable because the graph is random. Is it clear here? So we want to pick a sparse subgraph H. When we query H, that gives us H star. As I said, I have to also cover anything that we don't query. R is the induced subgraph of those edges. So, induced subgraph. We'll talk about induced subgraphs later. Okay, so R is a subset of any edge that we do not query. Right? So we have to find the minimum vertex cover of anything that we queried and was realized and anything that we didn't. No questions? Yes.
So you're not allowed any errors, right? So basically you have to assume that those edges exist.
Yeah. So we our only error between the approximation issue, right? So we allow an approximation issue to be one, but we want to make sure that our solution is one.
So condition on A star R is deterministic now.
Yes, so R is any edge in G, right, that you do not query.
So R is, I think, deterministic given based on H itself. You don't need to know H just star.
Yes.
R is just E minus H, so R is always deterministic.
Yeah, I mean, like, I thought the benchmark is the matching G star, not G.
Minimum vertex cover,
The very star, yes, G star.
so this is minimum vertex cover of G star opt, right? Just some simple basic algorithms and why they don't work, but if you query everything, that here doesn't work because our graph may be very dense. If we don't query everything, in that case, our approximation issue can be as bad as 1 over P. And interestingly, this algorithm may seem good, which is what if we query a constant number of edges for any vertex. This also is as bad as querying nothing, right? So we need to be smarter about it. So what I'm going to do is that I first talk about two simple two approximation algorithms. So two approximation algorithms, and then combine the ideas from these two to improve over that.
Version.
We go back to the trivial algorithms.
Yes.
Why does P show up in algorithm 1?
So here, let's say your graph is basically a matching, right? And each edge is realized probability. Right? So if you don't query anything, you have to cover all the edges.
Oh,
Right. But only, yeah. Okay, the first algorithm. Here, what we are going to do is that we first draw a random realization of our graph, which contains each edge with probability P sub E independently. So G1 comes from the same distribution as G star, right? But it's just something I kind of hallucinate, right? Why? Why does it come from the same distribution as G star? Because they both contain any edge of G independently with probability P sub E, right? And then we take minimum vertex cover of G1, which we refer to as P. Right? So P itself also comes from the same distribution as opt, right? Because G1 comes from the same distribution as G star, and P is minimum vertex cover. Okay, so what we do here is that we commit all the vertices in P to be in the final solution. So what it means is that now we don't need to worry about any edge that has an endpoint here. Okay, so we are going to query any edge that doesn't have an endpoint. I'll tell you why that you can't have many of those edges, but for now, let's agree that it's not very large. So I first take a minimum vertex cover of this random realization, commit all those vertices to the final solution, then query all the edges that do not have an endpoint in P, and return the union of P and minimum vertex cover of all the edges.
Wait, 90 hours. Yeah, maybe it's the baby or something. Oh, what is the toddler trying to learn stochastic approximation?
Okay, so in this algorithm here, I will show you an example to make it more clear. So say this is our graph G, right? We draw a random realization, G1, just take any edge independently with their given probability. So the first step is to take a minimum vertex cover of this graph. Here, the red vertices are a minimum vertex cover. So these will be our final solution. So get rid of all the edges connected to them. This is the top graph that we are going to query. So after querying that, this is our edge. After querying that, say these edges are realized, that's our edge star. Now we also take a minimum vertex cover of this graph, the green ones, right? So our output will be the union of red and green. And why is it a two approximation? I guess it should be clear, right? Because P comes from the same distribution as opt, right? So P has the same, the expected size of P is the same as opt. And here, what we add here is basically the minimum vertex cover of a subset of realized edges, right? So this minimum vertex cover cannot be larger than opt. So this plus this gives us a 2 approximation. Okay, now why now we need to talk about why H is not too large. So basically, a simple application of union bound is based on 2 facts. The first one is that H is an induced subgraph here, right? Why is that? Because I take a subset of vertices, I get rid of all the edges connected to those. So H is an induced subgraph over the remaining vertices. And the second fact is that none of the edges in H can be realized in G1, because otherwise you have to add one of the endpoints to P, and that vertex wouldn't be in H. Now take an induced subgraph with X edges. What's the probability of that subgraph being H? None of the edges should be in G1, so 1 minus P bar of X. Now, an application of union bound tells us that with high probability, H has at most N over P edges. Good? Okay, so I already proved that we query the small number of edges and also proved that it's a 2 approximation, but I'm going to make a slight modification to this algorithm to put it in a framework that we are going to work with today, and also present a different analysis for it, which you will see why. Okay. So the modification that I'm making here is that after I query H, okay, so H is a subset, contains a subset of edges, right? After I query that and get H star, I will also hallucinate all the edges that I do not query, right? And add that to G2. Why am I doing that? Because G2 now also comes from the same distribution as G star, right? So G2 contains any edge that was queried and realized, and also contains any edge that they do not query independently with probability P sub. So G1 and G2 are from the same distribution as G star, the actualization. And as a result, the minimum vertex cover also come from the same distribution as opt, and clearly that will give us a 2 approximation. Yes?
No, sorry, I don't think I got what is G2. So.
Query H, right? It gives you some edges. G2 is the union of those edges, and also contains any edge that you do not query, any edge that's not in G independently with probability P sub E, right?
Oh, okay.
So you want G2 to come from the same distribution as the actual realization.
So in some sense, this is worse than the previous.
Yes, exactly.
But
Because then you also have to cover these hallucinated edges.
yes.
Yeah. But still, it's a 2 approximation because now minimum vertex cover of this and this both come from the same distribution. But I'm going to talk about slightly different analysis, and that helps us to see in which scenarios this algorithm will have a performance. Right. So for any vertex, first of all, let's define this thing, which I'm going to use a lot. So let's remember that CV is for any vertex, CV of the vertex is the probability that the vertex belongs to the optimal solution. What does it mean? If you draw a random realization of the graph and take a minimum vertex cover of that, what's the probability that this vertex is in that minimum vertex cover of random realization? Is the definition clear here? We are going to work with it. So now what's the probability that this vertex is in the output of the algorithm we talked about? So you want to calculate the probability that a vertex is in S1, right? When would that happen? It should be either in P, which is the minimum vertex cover of G1, or in minimum vertex cover of G2. Right? So that would be 1 minus the probability that it's not in G1, minimum or square G1 or G2, which would be C2 times 2 minus, sorry, CV times 2 minus CV.
Okay, this is the probability that B is in S1.
Yeah,
S1.
is the output of the algorithm we discussed. Output of this algorithm.
Oh, that's S1.
Yeah.
Okay.
So it's S1 because I'm actually going to talk about some two.
Good.
Uh,
So, and for it to be there, I see.
okay. So now let's define a per vertex approximation ratio, which would be the probability that the vertex is outputted by the algorithm over the probability that it is in the optimal solution. Sorry, what's that here? It's going to be 2 minus CV, right? Because probability of B being the optimal solution is exactly CV. Cancel that. Okay, so this is a clear proof that the algorithm is to approximation like per vertex kind of, right? Yes.
Why is it independent if the vertex is in B versus it's within one separate G?
Because these two graphs, they are independent of each other, right? So G1 is just what is it? Independently, like it contains each edge of the graph independently with probability PE, and G2 is just sum of the realized edges, and it contains the rest of them each independently with probability PE. So G1 and G2 are completely independent of each other, right? G1 doesn't have anything to do with the actual realization. G2 has some things to do with the actual realization, but they're independent. Okay, but now the important point here is that if the CV is large, this algorithm is already better than to approximation, right? If for all the vertices, or even for an acceptable portion of them, this is large enough, this algorithm will already be better than to approximation.
And so what does that mean? If your vertex over of the graph is large already, it's like omega n size, this is already better than if the expected vertex over.
And that, so it can be omega n, but for any vertex, it can be like a constant, right? So it can be a vertex. For any vertex, it can be epsilon, right? But still the vertex.
But your approximation ratio
That
is the expected value of, like the heat you get, the improvement you have over two approximations, the expected value of CV, no? Is that correct or no?
Yeah.
I don't think so. So the approximation ratio that you get would be sum of this over sum of CVs, right? And the CVs won't cancel out like this.
I see.
So
Now this problem, we had these things before also, yeah, this. I think you're right, good. So the approximation, the value of what you get is summation CV2 minus CV of the summation CV.
yeah. But I think for a large, say a large portion of the solution, like half of the solution comes from vertices that have large CV, and say larger than half, then this would clearly be better than half approximation, two approximations, right? Because for, okay, we'll see. Okay, good.
But that's exactly the same as saying if the expected value is large, then a lot of the contribution will come from vertical.
Yes, large, I mean, like if it's, I mean, a large constant times n, that would be true, but if it's like epsilon n, that wouldn't help, because then for all of them, you would.
I think you lose a quadratic term here instead of linear term. Like the top one is a quadratic term, so.
Yes. Yeah, exactly. So your approximation.
It's like 1 minus summation CV squares over opt. So if opt is like uniformly distributed also, then what you're
Yeah,
saying is
so
good.
yeah,
If opt is
exactly.
clearly distributed, then.
So, yeah. So now, based on this intuition, now we're interested to design an algorithm that has a good performance if CVs are small. Let's do that.
Oh, yeah, sorry, but I saw all of this to say, isn't there Some of these vertices falsification allow you to assume CVs are large.
So large is usually a constant, right? For example, in matching, we can assume that your matching size of n. So omega.
Oh, I see. So if you wanted to only beat two, maybe you can use those. If you want to beat
Yeah.
well respectable values. Okay.
But I'm not sure if you can assume the same thing for any score. I haven't done it.
So the matching one doesn't work, but I think there are constructions that.
Now the second algorithm. So the framework is the same. We first commit a subset of vertices to the solution, then do the same thing, which is query everything that is not covered by P. G2 will be whatever was queried unrealized and hallucination of the rest of the graph. And then we would return the union of P and then minimum vertex score of G2. So we'll use the same framework for our future algorithms as well. It's just the choice of P that determines what the algorithm is and its output, right? So it's basically what are the vertices that you commit to the vertex coverage. So now here that P is all the vertices that have CV, which is the probability of joining the optimal solution, at least half minus epsilon. Now, epsilon here is a small number of things here. Yeah. First, let's see why the number of edges that we query is not large enough. Sorry, the number of edges that we query is large. The reason is that, let's say an edge is an edge, it means that it doesn't have any endpoint in P, right? So both its endpoints have CV smaller than half minus epsilon, okay? What does it mean? This edge, if you draw a random realization and a minimum vertex score of that, this edge will remain uncovered by that subset of vertices with probability at least 2 epsilon. Okay, this may be a little counterintuitive because I'm saying that there's an edge that's not covered by some minimum vertex cover, but that minimum vertex cover is a minimum vertex cover of a subset of realizations, right? But this edge is an edge in G, so it may not be realized. So it's possible that the edge will remain uncovered, right? So this edge will be uncovered, will remain uncovered with probability at least 2 epsilon when you take a random minimum vertex cover of a randomization. We already proved that the expected number of edges in G that are not covered by opt, which is a random minimum vertex cover, is O of n over P. So how many of these edges can you have? Linearity of expectation tells you that you can have at most O of n over epsilon. So the number of edges that you query here is O of n over epsilon. Good. So let's make sure that the algorithm is clear. This is clear.
Sorry, could you say again what a random NBC means in the first?
Take a random realization of your graph and a minimum vertex cover of that random realization. So this is a subset of vertices, right, drawn from the same distribution as opt, right? So we know that for any edge, it will remain, any edge that's not an edge, it will remain uncovered with probability at least 2 epsilon. But because each endpoint will join that subset with probability at most epsilon half minus epsilon, at 2 half minus epsilon is at 1 minus epsilon. Good. Okay, that's good. So now we are interested in analyzing this algorithm, so approximation, and also see when in these scenarios it will have a better. Again, our per-vertex approximation ratio. We know that we are taking any vertex with CV larger than half minus epsilon. So the per-vertex approximation should be here. This is 1 because you are always taking it. And this is CV. Right? But for the that have smaller CV, smaller than half minus epsilon, you're basically choosing nothing, right? Because they will not be in P. The only chance that they have to be in the solution is if they are in the minimum vertex cover of G2, which has the same polarity as being in opt, right? Okay, so what does it mean? Clearly, this is, actually, if I have it in the slides, yeah. Let's plot the function. Okay. So now if we plot this function, you see that here this is basically 1, and it peaks at half minus epsilon, right? And even in that case, it's upper bounded by 2 plus epsilon, right? So this clearly shows that the algorithm is in the worst case, 2 approximation, but it will have a significant performance if a large portion of your solution comes from here. Okay, now let's bring back the previous algorithm as well. So this is the per vertex, the approximation ratio plus. Okay, so here the x-axis is CV, right? And here is the per vertex approximation ratio. So for a vertex with some particular CV, this tells us what's the approximation ratio of any algorithm for that vertex. Is this clear? Is there any questions? Interesting observation here is that for any CV that you take here, at least one of these 2 algorithms, at least one of these 2 plots is at most 1.5 plus epsilon. But you can verify that. Here is the red one. From this area, in this area, the blue one is always smaller than 1.5, right? So what it means is that like, if each vertex could choose which algorithm is going to be run on that particular vertex, then you could get already a 1.5. But that clearly is not possible because you have to run single algorithm. But still, what you can do is to just like look at the structure of your graph, distribution of CVs, and pick best of these 2, right? And that would give you 1.66 approximation.
Can I ask you something?
Yeah.
So you were comparing E of alg over E of opt.
For any vertex.
Yes.
Yeah.
If you were comparing E of alg over opt,
Yeah.
this thing instead,
Yeah.
then this will become just E of summation CVs or something like that, no? That CV thing you had will cancel out here or no?
Okay, you're saying that it means my approximation issue, just in the setting. If it was
Yes,
this,
if I was looking that, then the per vertex guarantee, does it become just summation, like become 2 minus summation CVs? Or,
so regardless, this thing is just how much does it matter if it's inside or outside? Yeah, no, in that case, it's not. Yeah.
and the only reason I'm saying this quantity, even though they don't look like it, they are really the same as stochastic graphs because opt and alg are both actually, at least for matching, they are
Yeah,
all
they-
concentrated.
Yeah, probably here they should, but I don't see like how that's going to help with this.
But
the-
I thought maybe the second one allow you to do all those cancellations that you wanted per vertex. Like basically, instead of getting summation CVs and entire sum divided by entire sum, you get sum of CV times 2 minus CV divided by CV. But I'm not sure if that will happen.
So, so if we run the best of these 2 algorithms, it gives us 1.66, but that's not still ideal. You want to go down to 1.5.
So, okay.
Yeah.
And why do you get this? How do you get this quantity? 1.66?
You just do the math, but
Okay.
but it's clear how you can get 1.75, right? Let's say you hold a like weighted vote, right? And ask the vertex which algorithm you prefer, right? So half of them will be very happy, right? A weighted half.
Say half of
will
them will get
yeah.
this much. Good.
So that,
Oh, those things are never worse than two.
Yeah.
Okay.
but that's
Yeah, perfect.
still it's simple. But I'm going to talk about like how use these ideas to go down to 1.5. The idea basically is to combine these two algorithms and first, we'll pick a carefully picked threshold tau. I'm not going to tell you right now how to pick that, but let's say I give you how. Then we'll divide the vertices based on their CV to two parts. One part is the ones whose CV falls in this range between 1 minus tau minus epsilon and tau, and the rest are in the red area. Right? So we'll design an algorithm that treats these vertices as if they were in algorithm 1 and treats these as if they were in algorithm 2. Right? So the probability of this vertex being taken by this algorithm would be the same as that vertex being taken by algorithm 2, and the same for these, but algorithm. Okay. So now let's assume that we've picked tau. Let's not worry about how. I'll tell you how the algorithm actually works given tau. Again, we are only concerned with this choice of P. The rest is similar to before. So what we do is that P contains none of the vertices here, right? Because that's what algorithm 2 would do, right? It doesn't take anything that has a CV smaller than half. Okay? Because here we are kind of running out. Takes everything from here. That's what algorithm 2 would do.
Yeah.
But here, we are running algorithm 1, meaning that we take a random realization of our graph, take a minimum vertex cover of that, and any vertex whose CV falls in this range would only belong to P if it is in that minimum vertex cover. The rest is basically the same. Query all the edges that are not covered by P. G2 is the union of those and hallucination of all the remaining edges. And then return the minimum vertex cover G2 and P. Okay. Take some time. I guess that is algorithm. So I'm going to talk about the list of that. Okay, let's say my tau is half. What happens? I'm basically running algorithm 2. Right? Taking nothing from here, taking everything from here. Okay, let's forget about epsilon for now. It's just not very important here. Okay. And if tau was like 1, tau is always larger than half, between half and 1. And if tau was 1, I just run algorithm 1. But instead what I'm doing is that I'm treating the red area like algorithm 2 would do, take nothing from here, take everything from here. And when I'm saying from here, I'm talking about vertices whose CV is in this range, right? And the ones here, how do we decide if our final if P contains them or not? We take that random minimum vertex cover, a vertex cover of a randomly realized graph. This is what algorithm 1 would do. And then only take a vertex from this range if it is in that minimum vertex cover, right? Good. Should we continue? Okay, the first question, why is it that H is small? We already proved 2 things for algorithm 1 and 2, right? To show that those algorithms quite a few edges. The first one was that the expected number of edges not covered by a random minimum vertex cover is often over P. And the second one was that the number of edges that will remain uncovered by a random minimum vertex cover is the number of edges that will remain uncovered by minimum vertex cover probability at least epsilon is at most O of n over epsilon B. right? And here I'm defining CE, which is the probability that an edge is covered by opt. Again, opt is just a subset of vertices, and an edge being an edge in G being covered by that or not means that if it has an endpoint in that subset. Okay. So now, if I show that any edge in H is either uncovered by G1, okay, or it has CE smaller than 1 minus epsilon, then the proof of this is complete. Because the number of edges would be sum of this and this. Now, what was this claim true? What's the claim? Any edge in H is either either doesn't have an endpoint in G1 or its CE is at most 1 minus epsilon. Any edge in H clearly doesn't have an endpoint in zone 3. Okay. So both its endpoints are in zone 1 and 2. So now if both endpoints are in zone 2, it means that none of its endpoints were taken by G1, right? Sorry. Let's say there's an edge in H. Both endpoints are in zone 2. What it means is that none of the endpoints are in this minimum vertex cover, because otherwise that edge wouldn't be in H. What was H? The subset of all the edges that do not have an endpoint in P. So that's about the edges whose both endpoints are in zone 2. Now, what if at least one of the endpoints is in zone 1? In that case, CE, right? Clearly upper bounded by CCB, the CB times. Is smaller than 1 minus epsilon. Sorry, it's upper bounded by 1 minus epsilon. Why is that? Because one of the CBs would be at most 1 minus tau minus epsilon, the other one would be at most tau. Right? So the sum. And have is for the it doesn't really matter for the approximation ratio analysis. It only matters like for ensuring that H is not too small. On the other hand, tau doesn't matter here. Tau is only for the approximation ratio. Okay. So we are done showing that H is small enough, so we're not going too many inches. Now let's talk about the approximation ratio. So I'm going to, so the analysis is kind of different for zone 2 and zone 1 and 2. So we have separate analysis for this part and a separate analysis for this part. So let's first look at zone 1 and 3. So what's the probability of a vertex whose CV falls in this range? Sorry, so we're interested in understanding the probability that a vertex is outputted by the algorithm as a function of its CV, right? If CV falls in the probability that V is outputted by this algorithm is exactly CV, right? We discussed this when we are analyzing the algorithm. And if it's in this zone, it always belongs to the solution, so probability is 1. Now, let's define these two parameters. I define alpha to be the contribution of the vertices in zone 1 to the optimal solution. So it's going to be the CV, sum of CV of all the vertices whose CVs fall in this range, right? And I refer to those Z1, right? So Z1 are the vertices whose CV falls in zone 1, and Z3 are So alpha is the contribution of the diversity in this zone to the optimal solution, and beta is the contribution of diversity in this zone to the optimal solution. Right. Now, based on these, let's calculate the approximation ratio only in zone 1 and 3. So it's kind of hand-wavy what I mean by approximation ratio in this range, but let's go there. Okay. So the approximation ratio in this zone, I'm defining defining it as to be the expected size of the solution, but the expected, the expected number of vertices from zone 1 and zone 3 in the solution output by the algorithm over the expected number of these vertices in opt. Right. So S intersection with Z1 and Z3 and opt intersection.
This is 1 plus tau. Roughly.
So
Oh, no, sorry. It depends on the phone, but-
yeah, it depends on one, yeah. Okay, so it's going to be intersection of S and Z1 is alpha, right? Because each one, the expected intersection of them, because each one belongs to optimal solution. So it belongs to S and alpha, the same probability. So it's alpha. Now we are taking everything in zone 3. So the expected number of them is exactly the number of them. And here, this is alpha plus beta, right?
So Z3 is at most like 1 over tau larger than beta.
Yes,
Something like that.
yes.
Yes.
So now, because these versus in Z3, they have taus at least, sorry, their CV is at least tau, right? So how many of them can you have when the sum of CVs is beta? It's going to be beta, right? Okay, so now the choice of tau matters because that determines what alpha and beta are, right? So we choose our tau. Sorry, okay, so first of all, because we know that tau is upper bounded by, also lower bounded by 2, we can do this. Okay, now the choice of tau. We choose it in a way that alpha is greater than or equal beta, okay? There is always a tau like that. What is it? If you set tau to be 1, right, alpha and beta would be the same, right? So there is always such a tau. And we pick a tau that satisfies this property. However, not all of them would work because they also affect zone 2, right? So, but we'll ensure that this property is always satisfied. And when that holds, this thing is going to be at most 3 halves. Right? So we are done with analyzing zone 1 and 3. If we can show that the same thing, the same 3 halves upper bound holds for, if I had instead of Z1 and Z3, I have Z2, then putting them together to give me a boundary. Good. Any questions? Okay, so now I'm not going to tell you the whole analysis we're going to, just some rough ideas. That's the like, not very challenging, but the more involved part. Okay. Let's talk about the probability of any vertex being outputted by this algorithm in zone 2, right? We calculated that before. It's CV times 2 minus CV, right? Now to kind of analyze that, we'll assign each vertex a budget and a cost. Okay, what's the budget of a vertex? It's 1.5 times CV. Why 1.5? Because we are going for 1.5 approximation ratio, right? So each vertex can like cost us this much. Right? So we give it this budget, and the cost will be the probability that the vertex is output by the algorithm. So that's the cost that the algorithm has paid for this vertex. Right? So the sum of budgets. The sum of budgets would basically be the expected size of the number of vertices in zone 2 that are in the optimal solution, right? And the total cost is the number of vertices in zone 2 that are output by the algorithm. Right? So now our claim is that we can use the total budget of zone 2 to pay for its total cost. Okay, some of the vertices may have a larger cost compared to their budget, some may have smaller. We'll see about that. So if a vertex has CV larger than half, it will have a surplus. Its budget will be larger than its cost. And if it has CV smaller than half, the other. we have a deficit, its cost will be larger. Why is that? Let's calculate budget minus cost for any vertex. So this was the budget, right? 1.5 CV. And the cost is the probability that it's output by the algorithm. 1.5 CV minus the probability going to be CV times CV minus. So if CV is larger than half, it's going to be positive. If it's smaller than half, it's going to be negative. So the idea here is that to use the surplus of vertices in this range to pay for the deficit of the vertex. Now, to give you some ideas about that, I will show that take two vertices, U and V, right? One of them has CU equal to half plus x for some x between half and 1, sorry, between 0 and half. Right? And the other one has CV half minus x. Here, right? So CV falls here and CU is here in the mirror picture. So in other words, CV is 1 minus C. So now my claim is that the surplus of this vertex is the same as the deficit of this vertex. So you can kind of charge the cost of this, the remaining cost of this to the surplus. Let's just do the math. Use surplus, as we said, is CU times CU minus half. Now replacing CU by half plus x. Now the deficit is minus this term, because when it's negative. Doing math gives us the same thing. So now we are kind of interested to show that we have enough mass of, like, you have enough of vertices with the point here is that we were able to pay this deficit with U surplus, right? But they don't have to be like exactly, they don't have to be exactly like this. If CU was half plus x plus something, you could still, the surplus would be higher and you could still use that to pay for it.
This is like a quadratic term, and you're saying basically the worst case is when they're all happening at half.
Yeah, but
You're just shifting all the money.
that's where it was everything, the worst case is everything is half. But actually, it can also be bad if, like, I think you get the same thing for zone 2 if everything, like half of the mass is at some point half plus x and half of it is half minus x.
Yes, but you're kind of saying that this
Yeah,
has
it
the
doesn't-
same cost as if they were all.
Right. So now, so it matters how you pick to make sure that you can actually satisfy this claim, right? Because if I pick a tau that like only results in having some in zone 2, if I have only versus with this property, then I don't have enough surplus to pay for them, right? So the choice of tau matters. So we already said that to help zone 1 and 3, we need this property to hold, right? What is it? The contribution of these to the optimal solution should be at least the contribution of these to the optimal solution. So we know that this should be true. Tau should satisfy this. Now, to make sure that zone 2 is also okay, we need to pick tau to be the smallest number in this range. The smallest number in between half and 1 that satisfies this. That would ensure that for any mass that you have here, right, you also have at least the same number, the same amount of mass here. You'd be able to pay for these with these. So that would complete kind of our analysis. So here I just didn't talk about epsilon much because that's not very important for the approximation ratio. We needed that to make sure that the graph at the query is very small. Okay, now you may ask, I think about going beyond 1.5. I think it's possible, actually, but I don't know how. There's something that we need to know is that, again, if you want to go beyond 1.5, you need to make sure that your analysis really uses the fact that edges are realized independently. Here, and our analysis only use that to show that the expected size of the graph that we query is small. For our approximation ratio, we didn't use that at all. So I assume that if you want to go beyond 1.5, we need fresh ideas, at least the way these algorithms work. And another open problem generally is that we know that for matching and minimum vertex cover, both of them, this many number of queries is required, right? But we don't know what's the best approximation ratios that you can get using this number of queries, even for matching, despite the biggest side of it. For bipartite matching, we know this. For matching general graphs, this is under submission, this is 0.68. This improves your paper. Yeah, and
Second digit by one.
by 2, 1.4. Okay, but it also works for weighted graphs. Okay, and for minimum vertex cover, these are the known results, and it's really interesting to see whether they can be improved up to 1 plus epsilon and 1 plus epsilon. Thank you.
Can you repeat once more how the value of tau of x on 2? Because you said you have to pick something so that not all the words.
Yeah, I didn't really say that clearly, but let's say I'm picking the first tau that satisfies this, right? So if it's not a half, it means that like there is a larger mass here. At least half of the solution comes from here, right? If it's not a half, otherwise tau would just be a half. Okay, so have that. Okay. Now let's say I find this tau and it turns out to be here, right? So now if we take any x, let's say this is your x. Okay. So my claim is that the mass here, and by mass I mean sum of CBs for the vertices, CB falls here. For any x that you take, the mass you have here cannot be smaller than the mass you have here, right? Because then you could show that your tau would be smaller, right? So now, what he tells you is that for any mass that you have here, you have at least equal amount here, and you can always pay for them, for these. So that's basically.
Another question?
Things change if you allow adaptive.
That's a good question.
So is the lower bound?
And it should still be 1 n over the p, but I don't know even like we can improve. That's interesting.
You know what happens if you round the maximum degree to be 1 over p instead of n over p edges?
Okay, I think it should I think you should be able to do that with some modification to do that in this algorithm. I haven't really. Didn't you mention once that you think this can be done?
No, for matching it usually.
No, for me, for the
Vertex cover usually, I don't know. Actually, I'm very curious to see. Because for matching, you basically ignore the vertices that have a high degree and nothing bad will happen. For vertex cover, the moment you do that, you will not cover.
someone once told me that they have some ideas. I don't remember exactly. Okay, it wasn't you then, someone else.
Any other question? Now let's thank Mahsa again.
Thank you,
People are
everyone.
around for